Optimization problems. To introduce the idea behind optimization problems, let's think about pairs of non-negative real numbers x and y between 0 and 20 with the property that their sum is 20. What is the greatest product x, y? Now, the problems we do in this video are not difficult and can likely be done by reasoning. But we use the easy examples to introduce optimization. And then you take those ideas into the more difficult problems you come across in your field. The objective function is the function we wish to maximize or minimize. In this case, we want to maximize the product x, y. The constraint tells us to consider only non-negative values of x and y, satisfying the equation x plus y equals 20. What is the maximum value of the objective function subject to the given constraint? One approach could be to look at a table of possible scenarios. Here are 5 ordered pairs where x plus y add up to 20, and the product is given for each ordered pair. To use calculus to solve this problem, we rewrite the objective function using the constraint. Notice in the constraint that y is always 20 minus x. Whatever x is, y has to be 20 minus that value. So use that in your objective function. In the objective function, replace y with 20 minus x. And what did we get? What we got is an objective function now written in terms of just one variable. Notice that we're on a closed interval and that we have a continuous function. So we know by the extreme value theorem that this function has a maximum value on the closed interval. The only thing we have to do is check the endpoints and critical points. So how do you find critical points? Well, of course, you start by taking the derivative. In this case, it's going to be easier to distribute that x before you take the derivative. Otherwise, you'll have to use the product rule. After you distribute the x, go ahead and take the derivative. Now, to find critical points, remember you look for where p prime does not exist and where p prime equals 0. And this particular derivative exists everywhere. So just set p prime equal to 0 and you get a critical point of 10. Then, as I said, check your endpoints and your critical points. What's the objective function if x equals 0? What is the objective function if x equals 10? How about if x equals 20? Once you evaluate, you find your maximum value. The maximum product occurs at x equals 10, which means that y is also 10. So x equals 10 and y equals 10 maximizes p with a product of 100. This diagram very nicely shows you what's going on. The pink line is your constraint. The blue arc is the objective function. It gives you the height or the value of x times y for each ordered pair. But you're only interested in the product xy if the ordered pair xy is on that pink line. That pink line is your constraint. Let's introduce the steps of optimization. You don't have to follow these steps, but it's a nice kind of rule of thumb. So read the problem and then let's get started. Your first step is to organize the information, identify variables, and draw a picture. We're talking about a box here with a square base. So that's what I do. I draw a box with a square base, so W times W is my base, with a height of h. You identify the objective function. I'm looking for volume, so my objective function is W squared times h. Identify your constraints. You might have more than one, and write them in terms of the variables that you used for your objective function. I need to have that the sum of the length and width and height cannot exceed 64. So I just set it equal to 64. So the length and width, well, those are the same value. So W plus H. And I set it equal to 64. Express your objective function in terms of one variable. In this case, the constraint tells me that h equals 64 minus 2w. So I'm able to rewrite my volume, my objective function, in terms of just one variable w. Then find your interval of interest. W has to be 0 or greater, but it also has to be less than or equal to 32. Otherwise, you will it just doesn't make any sense. You end up with a negative volume. Then find your absolute maxima or minimum. To find the maximum or minimum, well, again, we're on a closed interval. So, and again, it's going to be easier if we rewrite v. So we rewrite v and take the derivative and look for critical points. We factor this so that when we set it equal to 0, it's going to be easy. The derivative exists everywhere, so just set it equal to 0 and we get a critical point of 64/3. Then remember what we do. We're on a closed interval, so all we need to do is check the endpoints and the critical points. You can see that our maximum occurs when W is equal to 64/3. You can also see that when W equals 64/3, I get a volume of 9,709 cubic inches. And here's a nice little picture. It's a graph of your objective function after you've written your objective function in terms of just one variable. And you can see that indeed we have an optimal solution when W is equal to 64/3. The objective function is maximized when W is 64/3 inches, which means that H would be 64/3 inches as well. With those dimensions, the volume is approximately 9,709 cubic inches. Now, in my YouTube station, I have other videos that have to do with optimizations. This video, the problems were kind of easy. You're going to want to see some more difficult problems, so do look for those videos in my YouTube station. Take care and have a great day.